jk can be represented as a vector. All the values of the function of x, y, z can be represented as a vector. So operate on a vector or a property to get data. Maybe this is gravity data. All right. There's a good class in EPS 109. And all they do in EPS 109 is they basically run computer simulations to take Earth models, some certain properties, to the data that you would expect to collect in the field. And this is becoming a huge part of geophysics. We call the process of going from model to data, we call that simulation. That's model to data. And we call the process of going back from data to model, we're going to call that inversion for the time being. And the method to my madness will be clear in a moment as far as matrices go. Okay. So model to data oftentimes can be represented as a simple multiplication of matrices. Anybody ever remember from your calculus a Green's function? You've heard of the Green's function in the calculus? This is often represented as a Green's function. Okay? This process right here is the way that we take, it's basically in signal processing terms, it's the impulse response of the transfer function of the system. So all these terms really go back to basic calculus. It's really interesting. But oftentimes we can take a Green's function, multiply it by a model matrix, and approximately get the data. And what we do in EPS 109 is we make that Green's function more complicated. So it becomes G of M, some complicated process. And this is simulation. The act of G operating on M is the simulation. And we can do that with pretty much any field. And really what it amounts to is solving differential equations. Imagine sending a seismic wave from me to you. Right? I basically can operate using the Green's function, which in this case would be the air between me and you. And you would hear something. Right? That's the data. So is the data that you hear the same as the data that, or the same as what's the model? Right? The model in this case is the voices. Well, actually, it's the air, I should say. Anyways, I'm digressing a little bit. The reason we use all this is that a lot of times, again, we we represent the process of going from model to data as a matrix multiply. And in matrix multiply, we have two matrices, A and B, and they're both vectors. It's not matrices, sorry about that. Imagine that A and B are both vectors. And let's say that A and B are column vectors. Right? In order to multiply them together, they have to have the same dimensions. Right? So let's say A is a 3-row by 1-column vector. B is the same. In A transpose B, right? If we use A transpose B, we get AD plus BE plus CF. So I always like to think of almost every process in mathematics as a matrix multiply or a vector multiply. Now, why do I think that? Well, that's how we do it in the computer, right? So when you, especially in MATLAB, right? Because MATLAB has the basic function of a matrix. So try to translate all of your, just as a fun exercise, I'd love you to do this as kind of a home exercise. Write f prime of x as a matrix multiply. Or write f double prime of x. Or write the integral of f of x from a to b dx as a matrix multiply. Kind of interesting when you think about it that way. What if f prime of x is equal to some matrix multiplied by f of x? Right? Some unknown matrix. How would we get back to f of x? What? We integrate it, but how do we do that in a matrix? Exactly. We have to find the inverse matrix to this matrix. And then we multiply that by f prime of x. Right? So integration, right, is the reverse of differentiation, which if we can represent it by matrix multiply, we simply find the inverse of the differentiation matrix, and we get the integration. Likewise, if we want to do two derivatives, what would we do? Suppose we want to do a second derivative. How would we do f double prime of x? Yeah, we just multiply another matrix in here of this one, right? We have two multiplications, which is just the square of that matrix. And then the inverse would be the inverse of the square. Okay, so this is really the way to think about this, because this is what MATLAB does. When it integrates something, this is exactly what it's doing. When it differentiates something, this is exactly what MATLAB is doing. So thinking in this way about simple mathematical processes like integration, differentiation, really anything, think and make. Okay, so the magnitude of the vector, right, is simply the square of the components summed together. And that's the other interesting thing. Whenever, so integration is f of x, but if f is digital, right, it's f x, x like that, I equals whatever to whatever. So anytime you see an f of x, and you think of it digitally, you can think of it as a sum. Well, if that's the case, anytime you see a sum, what should you do? Think of it as a matrix multiply. Okay, the dot product, pretty straightforward again. It's basically related to the